Well, that's good to hear. There's still time. All right. So we're talking about momentum. We're talking about impulse. I want to talk about, and actually I want you to do a little thinking about page 251, number 49, I think it is. So if somebody wants to read that for us. Oh. All right. So does anybody know what a ballistic pendulum is? No, it's not the one with the monkey again. This is a ballistic pendulum. You probably won't get the sound because it's probably coming through the ears. But we'll just pause it and we'll talk about what a ballistic pendulum is. And this is just a company that sells equipment for high school physics labs. All right. So this is a ballistic pendulum. Can you see it? Maybe we should go back. Here. I think it's a little easier to see this way. So what we've got, it starts the way it's starting. Over here, if you want to Google a picture of a ballistic pendulum, over here what we've got is a spring gun. So you take a marble that has a hole in the middle, a hole drilled through it. You put it onto, I don't know, I don't know what you call it. It's a shaft or something. And you push it in and it compresses the spring, and there's a little catch that's attached to the trigger. So I could walk away and the gun would be cocked. All right. And when I shoot the trigger, the ball is released. It's not going very far, so it flies straight. It hits this cup that's on a pivot, like a pendulum. So the ball leaves the gun, it goes into the cup and gets stuck because there's like a little flexible thing here, so it bends when the ball goes in, but it can't fall back out because the little tongue thingy doesn't bend that way. And then that makes the pendulum go up. It's an inelastic collision. Okay, and the pendulum goes up, and over here is this little thing that has all these little teeth. It looks like a very, 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 very small staircase. And there's something sticking off the bottom of my cup here so that the ball goes up and the pendulum gets stuck. So you know the highest height that it goes. And that's what a ballistic pendulum is. And usually in a ballistic pendulum, your job is to figure out what the speed of the object is as it leaves the gun. All right, so let's draw a picture for a minute here of all the pieces. So there's the gun over here. All right. And like I said, there's this shaft and a spring. Okay. And so that happens. There's this cup over here with this little groovy thing on the bottom. The ball goes, it gets stuck in the cup, and then there's I'll make it a different color. And then there's the tiny little staircase over here. And the pendulum swings up, and here's the cup with the ball in it, and the little tonguey groovy thing on the bottom gets stuck there. Okay, so everybody understand what happens? Yep, Gianni, Sari, you understand what's going on? Okay. So your job is to figure out what the initial velocity or the initial speed is going to be of the ball. I don't want you to solve this problem. I want you to think about and write down what you would do to solve this problem. Yep, so you're trying to solve the problem in the book, page 251, number 49. So if we were going to solve it, we would use all those numbers and things. But I want you to think about it and plan what you would do to solve the problem. And you need to write something down. You can do whatever you want, but I want you to write down in words. I want you to think about all the things that we've talked about. This really brings together oh so many, many parts of what we've learned so far. So think about what's going on, think about what's changing, and come up with a plan. I would use this. I would compare these things at these two positions, and then I would do this, and then I would do that. You're not solving the problem. You're just planning out what you would do. Assume there is no air resistance. Assume that the ball is moving so fast and that the distance between where the ball is released from the gun and where it hits the hanging cup is so small that we don't have to worry about gravity either. That the distance is small and it is flying for such a short amount of time that it is moving horizontally the entire time. Well, I'd like you to talk to somebody first and compare your ideas, because there's probably more than one way to do this. So I would say Elisa and Sari and Priya and Gianni and Zoe and Maddie. So compare your answers with that other person. And then yes, go ahead and solve the problem. So you may need to help Maddie along a little bit because she's going to still out of class. I'm not saying there's no gravity. I'm just saying that as the ball goes from here to here, it doesn't do this. So it's just going, it's moving fast enough and the distance is short enough that it doesn't fall. For this part, there's going to be gravity involved. But for this part, don't worry about how much it's going to fall, because you don't even really know what that distance is. Elisa and Sarah, you must talk to each other. You should get like 308. All right. What was the velocity you guys got for the box and the ball? Yeah, 1.5. Sure. Don't worry about it. I don't know what you did. All right. So now we want to talk about elastic collisions specifically. As you read, collisions come in two basic categories and then a subcategory. So collisions are either elastic, like this, or inelastic. And the difference between an elastic collision and an inelastic collision is what is conserved. So, for instance, in elastic collisions, not only is the momentum conserved, which it would be for any collision ever, but interestingly enough, the total kinetic energy is also conserved. Now, remember that when we're talking about kinetic energy, it's a scalar. So you have to take your velocities in all those different directions and turn them into a speed. Okay. For the record, and just so we have it all in one place, for inelastic collisions, only the momentum is conserved. Right? And there's a subcategory that we have referred to for inelastic collisions, which are complete inelastic collisions. And that means that either my two objects come together and move off as one big object, similar to the example that we just did with the ballistic pendulum. The bullet or the ball hit the cup and the pendulum, they stuck together and moved off. That was an example of a complete inelastic collision. And it also works the other way. I believe you had a homework problem where you had something that was stuck together and the spring popped them apart. So you started off with one object and it broke into two objects. Remember in physics that the physics doesn't care if you run the clock forward or the clock backwards. Whether I have two objects that start individually and become one object, or I have one object that breaks into two objects, the physics is the same. It's just a matter of where I put the I and where I put the F. And there's nothing in those equations that makes a difference for that. Okay? So for right now, we are going to focus on elastic collisions. And honestly, we're going to do a whole bunch of algebra. And you know how much I love algebra. It makes me happy. However, there will be some important results that we hit as we go through that are going to be important for you to remember. Some things I probably would not recommend you memorize, but we'll do some stuff. Okay? So, we're going to start with two objects. With different masses. We'll play around with the masses later. Moving with velocities v1i and v2i respectively. And so just because I'm going to have m1 moving this way and m2 moving that way. Now, because these are vectors, I can play around with the SIGN signs of v1i and v2i and turn this into anything I want. I can have them both going in the same direction, and that direction can be positive or negative. I can flip-flop m1 and m2. It doesn't matter. It's the beauty of the fact that they are vectors that you can change all that later. I'm just going to take a simple case. And your instruction is to find v1f and v2f after these objects collide. Like what? Like the activity that you did, yes. And we'll have to look at things. You will eventually do a lab on conservation of momentum. I don't know if it will be Monday. I feel as though Monday I'm going to need to use the long to finish this. So we may get a little out of sync with our labs and stuff, but that's okay because chapters 10 and 11 don't have labs that go with them. So, I probably know when the next homework is due. You should probably assume it's due. Oh, definitely. It's not due Friday. Yeah, towards the middle or end of next week. Oh, yeah. No. It'll be due next week. It'll be fine. We need to get through this. We need to finish up, but there are probably things that you can do. Okay. So if we assume that this is an elastic collision, and you need to be really careful when you're speaking. And if you notice, I always pause between an elastic collision or an inelastic collision. You need to be very careful about that. It helps to write it down. If this is the case, then I know that my initial momentum has to be equal to my final momentum, and that my initial kinetic energy has to be equal to my final kinetic energy, because that's what being an elastic collision means. Now, because this is just in one dimension, okay, so let's assume we've got one dimension. Just because it makes our lives easier, okay? That means that I can rewrite my momentum equation as m1 v1i plus m2 v2i is going to be m1 v1f plus m2 v2f. And just to keep things simple, I'm not going to put the vector symbols over the velocities, but know that you can make them positive or negative, or that they will come out positive or negative. And remember that what I'm trying to find are V1F and V2F. And so it's great that they both appear in the equation that I'm trying to solve, but unfortunately they both appear in the one equation that I have to solve. So what do I need? Well, I need another equation because I have two unknowns. So yes, I can now write an expression for my kinetic energy. And what is the formula for kinetic energy? So I'm going to have 1/2 m1 v1I squared plus 1/2 m2 v2I squared is going to be equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. And because I can and it makes my life simpler, I'm going to cross off, cancel out all my 1/2s. So now I do in fact have the same two unknowns in two equations, and theoretically I can solve this. Now to solve this and actually get an answer, there's only one way to do it. And if you do it the wrong way, you get something literally impossible. Like you'll take it to the, I tried that once. I started it the wrong way and told my class, go ahead, finish it. It's just algebra. You can do it. And they couldn't get it. And they took it to some of the math teachers who are like, no. So you have to solve this the right way. So you just need to remember that if you ever have to solve it again. So what I'm going to do, because I've been down this road before, is I'm going to take both of these equations and I'm going to put all the m1s on one side and all the m2s on the other side. Okay? So my momentum equation becomes m1 times v1I minus v1f, and the other side becomes m2 times v2f minus v2I. Right? Okay. Keep me honest. And I'm going to do a similar thing for my kinetic energy equation. So I'm going to have m1 times v1I minus v squared minus v1f squared is going to give me m2 times v2f squared minus v2I squared. All right, you with me? Okay. So, it may not scream it to you, but this and this scream factorable to me. And they are, right? So this side is going to be m1 v1I minus v1f times v1I plus v1f. Yes? And on the other side, I've got m2 is going to be v2f minus v2I times v2f plus v2I. If I FOIL it out, my inner and my outer terms cancel because of that minus sign, and I'm good. So, if I compare equation 1 and equation 2, you'll notice that I've got an M1 on the left-hand side of both equations and an M2 on the right-hand side of both equations. Yes? And I have V1I minus V1F on the left side of both equations, and V2F minus V2I on the right-hand side of both equations. I'm not going to substitute. I'm actually going to divide them. Sari looks scared. Because I know what's going to happen if I divide them. So what I'm going to do is I'm going to take equation 2 divided by equation 1. So I'm going to have M1 V1I minus V1F times V1I. Actually, I've got to start over here. M1 V1I minus V1F times V1I plus V1F is going to be equal to M2 times V2F minus V2I times V2F plus V2I. Make sure I got that right. And then I'm going to divide by the momentum equation, which was M1 V1I minus V1F. And on the other side, it was M2 V2F minus V2I. I can do that as long as I do the same thing to both sides of the equation. I'm just choosing what is convenient for me to divide by. So my M1s cancel, my V1I minus V1F cancel, my M2s cancel, my V2F minus V2Is cancel, and what I'm left with is V1I plus V1F is equal to V2F plus V2I. Which, if you think about it, might come in pretty handy.